Okay, so first of all, this might be some review for you guys. This is what the northern hemisphere looked like at the last glacial maximum, about 20,000 years ago. Okay, this is what Canada looked like. It was covered, the Ottawa area itself was covered under a mile thick of ice. Okay, so we of course got the big Laurentide ice sheet in eastern Canada and Accordion ice sheet on the west coast, and we got some ice sheets in Europe as well. Right? You guys know that, right? Okay. So I guess you could say at the last glacial maximum, Canada was just a giant ice cube, right? Now, some people still say that Canada is a giant ice cube. Okay, next. All right, so this is what the world looked like in the last glacial maximum. So, and this is what it looks like today. A lot of the world was covered in this continental ice sheet, okay? There was more water tied up in solid state. So you had water put into these big ice sheets, and there was water taken out of the liquid state, i.e. the ocean. So as a result, the sea level was lower by about 100 meters. It's pretty cool. So Australia was attached to New Guinea, and Alaska was attached to Siberia via the Bering Land Bridge. And also, so there's more water put into the solid state and it's taken out of the liquid and the gas states. So there was also less water vapor in the atmosphere. So there's less precipitation worldwide. And as a result, the deserts were more extensive and the rainforests more limited. Okay, it was a colder and drier place. Does everybody buy that? Hocus pocus? That makes sense. And I also want to point out that most of the landmass in the world is located in the northern hemisphere, okay? North of the equator, you find most of the world's land masses. Can everyone see that? Okay? So the northern hemisphere has a higher proportion of continents, and the southern hemisphere has a higher proportion of oceans. Now, it's easier to grow glaciers on continents or in the ocean. Fine. Very good. Very good. So it's easier to grow glaciers on continents. And why is that? You bet. There you go. Sorry, Yasmin. Okay, so what Sean said. So water has very high heat capacity. So that means it takes a lot of energy input to change the temperature of water. Okay? Water stores a lot of heat. People who live on the coasts, they tend to have milder summers and milder winters because the ocean kind of acts like a heat buffer, moderating the climate of people who live on the coast, whereas the heat capacity of land is relatively low, so it doesn't take as much energy to change the temperature of land, and therefore it can cool down faster and accumulate ice more easily. All right, everybody buy that magic trick? That's terrible. All right. And now I want to show you this. So this is one of my favorite graphs. Oh, just a sec. Maybe I'll make this an appropriate. There. Now it's a real PowerPoint. Okay, so this is one of my favorite graphs. This is illustrating the thermodynamic properties of water and ice. And so the horizontal axis represents temperature, from negative 30 degrees Celsius plus 10 degrees Celsius, and the vertical axis is a measure of depth. And the growth and decay of ice sheets depends essentially on two things: the accumulation of snow in the wintertime and the melting of the snow in the summertime, what we call ablation. Okay? So snow falls in the winter, and then some of it melts away in the summertime. And accumulation actually increases slightly with temperature of about 1 degree Celsius, because as you increase the temperature, you increase the amount of precipitation and more snow falls. Whereas ablation is actually exponential with temperature. So the warmer and warmer it gets, the more and more snow melts. All right? But given this graph, what do you think is the main controlling factor of the growth and decay of glaciers? Is it accumulation of snow in the wintertime or melting of the snow in the summertime? Okay. As for what what the main driving force behind the advance and retreat of ice sheets, okay? Is it winter accumulation or summer ablation? I'm going to give you a hint. It's summer ablation. So just picture this, okay? It rises exponentially. It doesn't really matter how much snow falls in the wintertime. If it's warm enough, you'll melt it all away. Okay? Does that make sense? Okay, so we're agreed, right? That's the main driving factor behind the advanced retreat equations. Just believe what I say. All right, next. Okay, so now I want to explain the what we call the oxygen isotope paleotemperature proxy. Okay, so you guys went over this in class, right? So it's isotope temperature proxy, and it works like magic. It's actually based on the water cycle and the isotopes of oxygen and hydrogen. So there's a couple stable isotopes of oxygen, oxygen 16 and oxygen 18. Oxygen 18 is about 500 times less abundant than oxygen 16, and it's heavier. Whereas oxygen 16, of course, is a lighter isotope. It preferentially evaporates. So it's more easy to evaporate oxygen 16. And depending on the temperature of the atmosphere, if it's warmer, more oxygen 18 is retained in the atmosphere. If it's colder, oxygen 18 is rained out. Okay? What do you guys call it? Rallying something rather? What do you say? Okay. Depending on the temperature of the air, the amount of oxygen 18 will either be retained or rained out. Okay? If it's warmer, it's going to be oxygen 18 in the atmosphere. If it's colder, it's going to be rained out. And so later on, this will be deposited as snowfall. And in ice cores, you have a higher oxygen 18 ratio. That means it's warmer. And a lower oxygen 18 ratio means it's colder. Does that make sense?
In the ice.
In the ice.
But in the ocean, it's like the opposite.
Yeah. Hey, you bet. Okay, so does everybody get that first step? Okay. So oxygen 18 is an isotope of oxygen. It's a stable isotope. Okay. Now, when it's warmer, you'll have more oxygen 18 being put into the air. Okay. So depending on temperature, the distribution of these different isotopes of oxygen will change in the air, the water, and the ice. Okay, so if it's warmer, you get more oxygen 18 in the atmosphere, and later on it will be deposited as snowfall. So when you look at ice cores, if you have a higher oxygen 18 ratio, that means that the temperature of the air was warmer at that time. Okay? All right, opposite with the ocean setting. So there's little marine organisms that make their shells out of calcium carbonate using ocean water. So if it's warmer, this takes more oxygen 18 out of the water and into the atmosphere, which makes the ocean oxygen 18 depleted. So if it's warmer, you're going to have less oxygen 18 in the ocean, and then when they die and their bodies are deposited on the ocean floor, and you look at them under a microscope, and you do your little mass spectrometry measurements, you have a low oxygen 18 ratio, that means it's warmer, and a high oxygen 18 ratio means it's colder. But it's all based on the water cycle, okay? So the distribution of these different stable isotopes of oxygen will will indicate the temperature at that time. Okay? Okay, we're going to move on. Right. Next. Okay, so this is all oxygen 18 measurements. Okay, so this is one of my favorite graphs. This is temperature from the Greenland ice cores, all the way from 20,000 years ago to the present day.